So we're doing great so far. We know for polynomial, rationals, radicals, trigonometric, exponentials, and logs, plug it in. As long as it exists, you're good to go, but it's not always going to happen that way. So what do we do when things start not working the way that we want it to? Let's look at an example here. So here's example 6. It says find the limit as x approaches 1 of x cubed minus 1 all over x minus 1. Notice this is a rational function, the limit of or a quotient. The limit of the quotient is quotient of the limits. So I can plug it into the top, I can plug it into the bottom. Those are both polynomial functions. And I want to physically see you trying to do that. I should see you trying to plug it in. 0 cubed, sorry, it should be 1 cubed minus 1, right? Plug in the x value. So it should be 1 cubed minus 1 all over 1 minus 1. And notice on top I get a 0 and on bottom I get a 0. This is a very special form. This is called indeterminate form. I mentioned this in the previous section. What does that mean? It means it's undefined at that point. And if it's undefined at that point, that does not mean that the limit does not exist, okay? It doesn't mean the limit does exist, but it doesn't mean the limit doesn't exist. Just because you get 0 over 0 does not mean the limit doesn't exist. It means we have more work to do. In fact, this is the exact problem, that we did in section 2.2. We've already evaluated this limit, okay? The way we solved this limit is we looked at it graphically and by using a chart. Now I want to show you how could have we done this exact same problem if we didn't use a chart. Well, here's one thing that I need you to remember. I need you to remember the sum and difference of cubes formula. And this was on the review. If you did the algebra review or the functions, lines and functions review, you would have seen this on that. So what is the formula I'm talking about? It's a cubed minus b cubed. If you have a cubed minus b cubed, what does that factor into? Well, it factors into, if you remember the saying SOAP, same, opposite, always positive. Same, opposite, always positive. That gives you your signs. So that would be the negative, the positive, and then the positive. Same, opposite, always positive. It's the first minus the second, then it's the first squared, the first times the second, and then the second squared is what it is. So that's what it is when you factor it, and if you look at it, our numerator x cubed minus 1 is a difference of cubes. So let's rewrite this limit and let's factor out that numerator using the difference of cubes formula. So this would equal the limit as x approaches 1 of the first, this is in the numerator, the first, which is x, minus the second, which is 1. The first squared would be x squared. And then we have to do plus the first times the second, which would be x times 1, which is just x. And then it's plus the second number squared. 1 squared is simply 1. So that's what the numerator factors out into. The x cubed minus 1 factors into x minus 1 quantity times x squared plus x plus 1. Again, please review your factoring of cubes, difference of cubes, and sum of cubes if you have any issues with that. And you could also distribute it to double check. But then on bottom, we still have that x minus 1. So why did I go about doing this? Well, notice in the numerator and denominator, we now have common factors. Remember, you can only simplify factors. So I have common factors here. So this would be the exact same thing as the limit as x approaches 1 of x squared plus x plus 1. The reason that we can do this is because these functions are equivalent everywhere except at the number 1. But it's perfectly fine because we don't care what happens at the number 1. We only care what happens near the number 1. So there is a limit rule that allows us to do this. We can plug it in because it doesn't matter what happens at that point. It only matters what happens near that point. So now because this is a polynomial, we could simply plug it in. 1 squared plus 1 plus 1. 1 squared plus 1 is 3. And we would get a final answer of 3. So if you look at the previous section of notes, you can see that this is exactly what we got when we did the table of values. We did values like 0.9, 0.99, 0.999, and we did 1.1, 1.01, 1.001, and we were looking at these values, and we saw that our y values were approaching 3. So we now have two ways of solving the exact same problem. One of them using a table, one of them using algebra by factoring. Okay. So the next thing says a strategy for finding limits. It says learn to recognize when limits can be evaluated by direct substitution. So what we're talking about here is polynomial functions, rational functions, radical functions, our 6 trigonometric functions, our exponential functions, and our logarithmic functions. All of those we can directly plug in the x value as long as it exists at that point. It says when the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all x other than x equals c. What they're talking about here is, in other words, simplify the dang thing. Instead of doing x cubed minus 1 over x minus 1, factor and simplify first, and then plug it in. Okay? And that's what the problem 2 says. And number 3 says, look, if all else breaks loose and you get totally stuck, you could always use a graph or a table to reinforce your conclusion. So make sure that your answer is correct always by just use that table in your graph, in your calculator, use that table feature, plug in that 0.9, 0.99, 0.999 for instance, and make sure your y values are approaching the same. So that's a nice way for you to check your answers.